they had struck so accurately. Deep Impact's payload had been traveling at 37,000 kilometers per hour and had struck with a force of 19 billion joules of kinetic energy. This produced the bright flash you see here, the energy of which is roughly equivalent to 5 tons of TNT. This flash was much brighter than scientists expected. It lit up the surface of Temple 1. However, ironically, the success of the first part of the mission caused an unexpected negative side effect. A large dust cloud was kicked up by the impact, which obscured the flyby's view of the impact crater. Dust outgassed from the comet for the next 13 days, peaking 5 days in, which made it hard to see the results of this interstellar bullseye. Although it did offer some interesting insights into the internal pressures going on inside the comet. Around 5 million kilograms of water and between 10 and 25 million kilograms of dust were ejected from Temple 1 in that time. Fortunately, scientists were able to rely on other eyes, at least to capture images of the explosion. The collision had been observed through numerous other telescopes on or around Earth, including Hubble, Swift, and even many amateur astronomer telescopes. Still, this was a serious problem. Although this outgassing was fascinating to record, the primary purpose of the Deep Impact mission was to take photographs of the crater caused by Deep Impact. Without images of the result, many of the questions about Temple 1 would remain unanswered, like about its structure and composition. Like a partially unwrapped gift, Temple 1 had been opened, but it had not yet been seen what lay inside. Some other craft would be needed to complete Deep Impact's unfinished mission. Fortunately, another craft capable of doing so had already been launched, and, having completed its own previous mission, was now drifting serenely through space. It was about to receive another task. It's time to talk about Stardust. Let's go back to the late 1990s, when cometary science was even more patchy. Although by this point we had sent 6 probes up to visit these enigmatic celestial bodies, not very much was known about their origins. It was believed at the time that comets were foreign visitors to our solar system, older than the sun, having been formed from the loose pre-solar grains of dust that orbit other stars, before drifting through space towards us, only to be caught up in the sun's gravitational pull. It was believed that this theory could be confirmed by traveling to one of these comets and picking up some of this loose dust, or stardust, that surrounds them in space. By examining the isotopic composition, scientists would be able to tell if it was unusual when compared to the dust given off by our own star. However, this was a challenging mission. As is often the case, it came down to a question of speed and energy. Comets travel through the inner solar system at speeds reaching 160,000 kilometers per hour. While it was possible for a probe to try and match that speed and come up alongside it, this had to be done without needing too much fuel, or the weight of the craft would be too heavy and thus too expensive to get into space in the first place. Initially, Stardust had nothing to do with Temple 1. For this mission, scientists selected a comet known as VIL-2. They believed that they would be able to get Stardust alongside VIL-2 at a relatively low velocity. However, this velocity would still be around 6.5 kilometers per second, or 23,400 kilometers per hour. As you can imagine, catching even particles at that speed would be extremely challenging. Although particles would likely not do too much damage to Stardust, being too small to really impact it, it would do irreparable damage to the particles themselves. When an object crashes at 23,400 kilometers per hour into a surface, the odds of it keeping its original shape and structure are incredibly small. Scientists would not learn much about the structure of these particles if they smashed those particles into pieces, not to mention the warping effect all that kinetic energy being suddenly converted into thermal would have on the molecular bonds involved. So, what was their solution? What was their mechanism for catching objects traveling at those speeds? Well, much like how an airbag softens the blow for you if you're involved in a car crash, scientists realized that they would need an airbag of their own, something that would not halt the particle all at once, but would reduce its speed over a longer distance, thus reducing the amount of crushing deceleration involved. For this, they found an incredible material that was basically air, solid air. They decided to use aerogel. Aerogel is a fascinating substance that was discovered in 1931 by Samuel Kistler when he made a bet with fellow scientist Charles Leonard about jelly. As you've probably seen if you've ever made it yourself, jelly is formed of 2 parts. Firstly, a relatively solid structure that acts like a kind of sponge, and secondly, water. When you add water to solid cubes of dense jelly, it absorbs the water and expands into the wobbly substance we're familiar with. If you were to extract the water, the solid part of the jelly would normally contract again. Kistler's bet with Leonard was to be the first one to remove all of the liquid from the jelly without making it shrink. In short, to make a jelly that was entirely filled with air, an air jelly. Without going into all the details, Kistler won his bet and at the same time invented the first aerogel. Aerogel is a fascinating substance as it is usually over 99% air and yet has the structural strength to support bricks. Nowadays, it tends to be made from silica composites rather than jelly, but can be made from a wide range of materials. It is incredibly light and is, strangely enough, an even better insulator than regular air. And most importantly for Stardust, when particles hit it, it would offer just the right amount of resistance to slow down the particle without denaturing or destroying it. The trails left behind in the aerogel would also be useful for scientists to spot where a particle had been captured. Stardust was fitted with a tennis racket-sized aerogel collector tray made up of 90 blocks of aerogel 3 centimeters thick, with over 1,000 square centimeters of surface area, which would be deployed from inside the main body whenever sampling was to take place. Stardust would also capture from the interstellar medium to allow comparisons and to learn more about the dust in our own solar system. Once it had collected these samples, it would store them on a sample return capsule, which would be fired back towards the Earth for re-entry and collection. This SRC was 80 centimeters by 50 centimeters, weighed 45 kilograms, and came fitted with an aeroshield, navigation recovery aids, and a parachute. Also on board Stardust was a navigation camera, a cometry and interstellar dust analyzer, and a dust flux monitoring system, among other scientific devices. The probe launched on the 7th of February 1999 and spent the next 5 years traveling through space, passing the asteroid 5535 Anne Frank along the way, which it took some photos of. But on the 2nd of January 2004, it finally arrived at its target, Comet VIL-2. And what it found was immediately extraordinary. Scientists had not expected much from VIL-2. Some NASA scientists described their expectation of it to be a rather bland object looking somewhat like a black potato. However, this is not what they found. Instead, the surface of VIL-2 was covered with spiky pinnacles hundreds of meters tall, cliffs, massive holes jetting dust and gas out into space, even on parts of the comet that were pointed away from the sun, and thus were expected to be less reactive. In short, the surface of the comet was unexpectedly alive and self-renewing. Something else was just as notable for its absence: craters. Unlike almost every other body in our solar system with surfaces exposed to space, there were no craters on the surface of VIL-2. This puts it in stark contrast to places like Mars or our own moon. Given the period of time VIL-2 is thought to have existed, it surely must have encountered other objects which impacted with it. So where had these craters gone? It shows that the comet's surface can either be self-renewing or active, reducing signs of visible craters over short time frames, astronomically speaking. And of course, during this flyby, Stardust had its aerogel collector exposed, and it was rapidly collecting dust samples. Just listen to the frequency in which dust struck the spacecraft. The samples were carefully stowed away, and upon reaching the vicinity of Earth, Stardust ejected the SRC. The angle of approach had to be just right, as it was traveling at tremendous speed. If the approach angle was too low, it would just skim off the atmosphere and fly back into space. If the angle was too high, the heat would disintegrate the capsule. So it was with great relief that the DC-8 NASA airplane monitoring the sky saw it approaching at just the right second and just the right angle. The SRC landed in the Utah desert where it was recovered, everything having worked and deployed just as it was designed to. And taking the samples back to the lab, scientists learned another completely unexpected fact about Comet Ville 2. It was not a visitor to our solar system at all. Unlike what had previously been believed, Comet Ville 2 had not originated from another star. It had been born from our own. By comparing the isotopic composition of the particles Stardust collected with the samples from our own solar system, it was proven that Comet Ville 2 originated from the solar system. And contrary to what all the ice on its surface might lead you to believe, the rock at its center was formed under white-hot conditions. Chondrules and calcium-aluminium inclusions were both found among the samples Stardust collected. These are structures that only form under incredibly hot conditions and can be found in other asteroids between Mars and Jupiter. So scientists had to rethink their theory that comets formed in cold conditions at the edge of solar systems, even if they do spend some time there. Both fire and ice go into making comets. And thanks to the careful, delicate way that the particles had been collected, scientists were able to find out one last surprising thing: the amino acid glycine. Amino acids are the building blocks that make up proteins, that are vital for all living things. Although this does not mean that there was anything alive on Comet Ville 2, this does lend weight to the idea that it was from comets such as this, crashing into our Earth millions of years ago, that life's first building blocks found their way to our planet, which I'm sure you all agree offers a tantalizing glimpse into our own origins. Given all these discoveries, you might have been forgiven for thinking that Stardust's work was done, but NASA is always reluctant to waste perfectly good spacecraft if they have more to give, and Stardust still had fuel in the tank. And so, when the question arose in 2006 of how NASA could capture that close-up image of Temple 1, Stardust's name was put forward. This would prove to be an interesting opportunity. Stardust was calculated to have enough fuel to make a 6-year journey around the solar system to arrive at Temple 1. This would represent the first time a comet was visited and then revisited years later, providing an intriguing chance to see how Temple 1 had evolved over the intervening years. Deep Impact only imaged about 1/3 of Temple 1's surface as it flew past, but even that was enough to identify fascinating geological features: layered terrains, smooth flows that contrasted sharply with the rougher terrain around them, crater-like vents and cliff faces. It would be incredibly insightful to see how these had changed in the time Temple 1 had orbited around the Sun. Stardust would be able to take images of things previously unseen, giving even greater coverage of the rich geological history of the comet. There were other advantages to using Stardust. It would be significantly cheaper to use equipment that had already been launched than to develop and launch something new. Stardust shielding was even designed specifically with cometary exploration in mind, which certainly came in use for reasons I'll go into later. It had all the camera equipment it needed to take precise images, and so Stardust was approved and was given a new name to match its new assignment: the Stardust New Exploration of Temple 1 mission, or Stardust Next. Of course, achieving this goal wouldn't be easy. Course corrections had to be made years in advance to conserve fuel and make sure Stardust arrived when it was supposed to. This made things complicated, given that Temple 1 didn't just remain static as it traveled. It spins once every 40 hours. So it wasn't just a case of figuring out how to get Stardust to meet up with Temple 1. NASA had to make sure it happened when Temple 1's impacted side was facing the Sun and facing Stardust once Stardust flew past. In effect, even though Temple 1 was not easy to see clearly, they had to calculate all the spins that Temple 1 would make a full year ahead to ensure the arrival time matched up. With Stardust's diminished fuel reserves, there would be little room for error. Incredible precision and excellent models would be required. As such, NASA enlisted the help of dozens of observatories around the globe. Temple 1 was little more than a tiny dot in the night sky, thus it was impossible to track through its surface features, which were indistinguishable at that distance. However, its asymmetric shape meant that its brightness fluctuated as it traveled, dimming as a narrower profile was pointed our way, then brightening as the wider profile rotated into view, in regular intervals that allowed a detailed model to be created with a high degree of certainty. Scientists counted the spins as Stardust traveled: 1, 2, 3, knowing that if they missed a single count, it would potentially mean the failure of the primary mission objective. Their model needed to be perfect. Stardust traveled for years through space, engaging in one Earth gravity assist and multiple laps around the Sun before timing its final maneuver a full year before it would arrive at Temple 1. The burn would alter its arrival time by a small, yet significant 8 hours. Stardust was now locked in. A year later, as it closed in on the comet, Stardust shields began to detect sounds as tiny particles began clattering off it. Temple 1 was still ejecting dust and small rocks into space. Stardust was hit dozens of times. Although these rocks were tiny, only a millimeter at most, some of these hits had enough force to go through the front of Stardust, cutting through a graphite cyanide honeycomb sheet as thick as your finger. Still, Stardust survived the barrage, and on the 14th of February 2011, Stardust made its flyby. It passed at a distance of 181 kilometers and took 122 images. I find it amusing that scientists waited for another holiday for a Temple 1 visit. They'd chosen Independence Day for their initial impact. Here, on a less violent visit, they chose Valentine's Day. Scientists had to wait for hours for the images from Stardust to arrive back, but when they did, NASA saw that they'd managed another bullseye. They'd correctly predicted the rotation of Temple 1 to an accuracy of a single degree. Right on Temple 1's surface was the crater that had been left by Deep Impact's payload. The mission was a success. From the images Stardust took, scientists were able to calculate that it was approximately 150 meters across, so 50% larger than they were predicting. From this, they learned that the surface of Temple 1 was a very fluffy material, made from more dust than was expected, and finer in substance than a powdered snowbank. The surface was incredibly porous. In fact, they were able to estimate that 75% of the comet was actually empty space, the whole thing held loosely together by gravitational forces. From analysis of the plume that had been ejected from Temple 1 after the impact, scientists were able to identify several interesting material components, including clays, silicates, sodium, and even organic material. While not life itself, these heavily rich carbon materials may have been carried to Earth by comets in the past, providing the vital materials that make up life here. Not only that, but they were able to see other changes that had taken place on Temple 1's surface. 3 pits that had formerly existed had merged to become one. A cliff face had eroded back around 20 to 30 meters. This indicated that Temple 1's surface was a dynamically changing place, leading to interesting questions about how these formations had formed in the first place that scientists could now puzzle over. So, Deep Impact's mission finally had closure, and had been a resounding success. But this was not the end for Deep Impact. Following in Stardust's footsteps, Deep Impact's flyby was later given a new mission entitled Epoxy, or the Extrasolar Planet Observation and Deep Impact Extended Investigation, which in 2007 saw it heading off to investigate other comets and taking hundreds of thousands of photos before ultimately dropping out of contact in 2013. But by then, Deep Impact had already done significant amounts to advance our understanding of comets and our solar system. What about Stardust? After its extended mission, scientists saw that there was still a little fuel left in its tank, so it ran with it. Firing it for as long as it could, scientists checked to see if their models of how much fuel Stardust held matched up with the reality. To its last breath, Stardust kept doing science until the end. When at last all its fuel was used up, it sent one last transmission to Earth to acknowledge that it was being turned off for good. Now, it finally